Right, thank you, Greg. So I want to start, like everybody else, thanking Christoph for organizing this wonderful event that's brought us all together here. I realize it's warm, we're tired, it's late in the day, so I'm going to try and keep my presentation as lively as I can. Feel free to interrupt me if anything isn't clear. And yeah, I'm going to basically tell you about a bunch of ideas and a bunch of people who you may not be very familiar with, the organicists, that I've been essentially looking at for the past. Is there a camera?
Yes.
Oh, hi. I didn't see. All right. Should I look at the camera now? I like to move around, so it's good. So I've been looking at these people for more than 15 years. I'm not going to try and tell you today why I think that there's much to be learned about the ideas that these people proposed about 100 years ago. You can read my work if you're interested, and I'm not the only one who's been in this project of rehabilitating organicism. Instead, what I want to do today is talk a little bit about the organicist movement as a movement, to understand what really motivated them to want to develop a new theory or a new account or a new philosophy of biology, and what happened to it. And as you can tell from my title, there was essentially an attempt to completely change, revolutionize biology by these people, and it didn't really succeed. It was a failure, so this is why it's a failed revolution. And so I want to understand why it failed and there was a revolution, but it wasn't an organicist revolution, right? So I want to talk a little bit about that. And this is part of a sort of a wider project, or more ambitious project, broader project, I should say, of looking at the relationship between biology and physics. Because it turns out the thinking about the dynamics of biology and physics, especially how biologists position themselves with regards to physics, provides a very useful framework to think about many developments in biological theory over the course of the 20th century. Some of that was already present in Mohang's presentation, right? So I'm going to be talking a little bit about that. And even though this is a very pessimistic title, I do have a little added a little question mark at the end, very timid one, because I want to suggest at the end of my presentation that maybe this revolution is perhaps now finally upon us, or at least the prospects of it have never seemed more clear, or more. The reasons for optimism, I think, are solid. But before I can do that, I think I need to talk a little bit about what I mean by organicist. Okay, this is a label that has taken many forms. It is used in different contexts. I mean something very specific by this term. And I think it's important to be specific about your labels, because otherwise, especially historians, professional historians, are going to tell you, it's not a good idea to have these labels that you project back into actors that never use these labels. I think Johan made a comment along those lines with regards to vitalism. So this is a term that I think is legitimate to use in the context of the authors that I've looked at, because it's a term that the authors themselves use to describe their views. Okay, right. So yesterday evening, Dalia was kind enough to show us where Hegel did his homework, the bar where he used to do his homework. So at the bar, Dalia asked about this known label of organicism. So I figured I would begin by talking a little bit about that. It is a term that I think can lead us astray if it is not clearly defined. And I figured that the best way to describe what I think we need to do is with an example. Okay, so consider this book that came out a year or two ago. It's the final book, I think, by Michael Ruse. And notice the title, The New Biology, a battle between mechanism and organicism, right? I was actually asked to comment on this book at the last dish in Toronto. And if you open up the book, you find, actually, there isn't that much about mechanism, explicitly about mechanism and organism. You can read that from where you are, but only chapter 1 and 2 are specifically about mechanism and organicism. And I just wanted to give you a sense of what can happen when we don't put leashes on the labels that we use to describe the ideas that we want to talk about. So if you then take the second chapter, Organism Strikes Back, and look at the table of contents there, this is what you get, which is an incredible sort of cocktail of different people with very, very different views, right? All put together under the label of organicism. Um, if I'm here, is that okay, Christoph? I'm still in front of the camera. Um, notice, right? So you got the German Romantics. You got Spencer, interestingly, vitalism as part of organicism. And then when you look at that subsection of the chapter, it's a discussion of Bergson and Whitehead. So even more weird, right? Having Whitehead as part of the vitalist there, and then genetics, and then one subsection of organicism. So anyway, it looks really, really strange that one can have a robust understanding of what organicism means if you look at this particular book. Okay, and this is not. I don't want to pick specifically just on this book, but there is, I think, a tendency of using these terms in a very broad sense, and that can just lead to confusion. Because if I say I'm an organicist, or I believe in the organicist ideas, you may not know what the hell I'm talking about until I explain what it is that I mean by that, right? So in that book, the term organicism seems to be used, as far as I could gather, to refer to this idea that the metaphor of the organism as a metaphor, right? So if you think of the populations as organisms, or the world as organisms, or the universe as an organism, you could maybe say that people who have believed those, or who have defended those tenets, are all organicists, right? And I think, yeah, this just is confusing, right? Not only because this is, of course, a historical term that we're projecting back to talk about Wheeler, Lovelock, and Whitehead in ways that maybe suggest more convergence than there actually is. And the situation is made worse because in biology, or in the history of theoretical thinking about biology, organicism has actually a really specific meaning. It refers to a group, a collective of individuals who were basically dissatisfied with both mechanicism and vitalism in the early 20th century, more specifically during the interwar period, and who tried to sort of develop a new theory, a new philosophy of the organism. Okay, so this is what I mean by organicism. It's a very specific meaning, okay, and it's actually different from all of the above. So when I'm talking about the organicist revolution, I'm not going to be talking about Wheeler or Lovelock or Whitehead. I think we're going to get a talk about Whitehead tomorrow. So I'm going to be talking specifically about those who describe themselves as organicists in the early 20th century, okay? And they saw themselves as trying to develop a sort of as they saw it, a post-mechanicist, post-vitalist philosophy of biology. And if you do a bit of playing around with, this is Google Ngram. You look at the number of books and articles that with the term philosophy of biology over the course of the 20th century. What you find is, unsurprisingly, right, when the field becomes professionalized in the late 60s and early 70s, there's a sort of upsurge of the notion of philosophy of biology. But interestingly, you also have a little local peak in the interwar period, right? So that's, again, some evidence that the term is, first of all, not anachronistic to use this term before Hull and Roos and people who we think of the first philosophers of biology. And so that already gives us a sort of an entry point. So what is this movement, organicist movement? Well, it is an attempt, as I already said, to reformulate the philosophical foundations for biology, and it was promulgated by a collective of people who read, discussed, and engaged with each other's work. I'm just mentioning here some of the most well-known and important exponents. Some of these people have already come up, I've noticed, over the past 2 days. So Craig mentioned to me John Scott Haldane over lunch, and E.S. Russell was mentioned by Philippe, and Woodger was mentioned as well. So, and Bertalanffy as well. So, these, as you can see, there's John Scott Haldane, born in 1860. So, he's on one of the earlier exponents, but then you have many other organicists born around 1900, right, and who sort of coalesced and developed their ideas in conversation with each other. Okay, is that all right? Is that working now if I do this? Yes, it does. All right, so I remember when I was trying to publish, I wrote a very, very long paper about Woodger, a 50-page paper, just saying that Woodger's ideas needed to be reappraised. And one of the reviewers said to me, said, look, this is just really anachronistic because there is no philosophy of biology before Hull and Roos. And the nice thing about doing historical scholarship as opposed to philosophical scholarship, where there's always an opportunity for the reviewer to get back with another argument, is that you can just present them with evidence. Okay, so I just presented with this evidence of a paper published in 1928, titled Recent Developments in the Philosophy of Biology. It's a review article, okay, published by Joseph Needham. And there he actually mentions organicism as one of the most important standpoints, he says, one of the most important factors in these considerations at the present time, okay? If you look at some of the other books, so this is a lovely book called The Riddle of Life by William McDougall, who's actually a psychologist. There was a sort of a survey of theories of life, and there he says there's now a large number of biologists who give addition to what is called organicism, or the organicist, or organismal or organismic doctrine, okay? So why am I showing you this? Just to show you that I'm not putting words in people's mouths. These are terms that were used at the time by the actors that I'm describing. So one of the perhaps easiest ways of thinking about what organicism was about is to understand what they were doing as an attempt to move beyond the impasse, or the conflict, the long-standing conflict between mechanicism and vitalism, to offer sort of third way that would offer the best of both worlds, okay? And if you look at the organicists, this is how they describe it. So here's Needham. Organicism combines the insistence of vitalism on the real complexity of life with the heuristic virtues of the mechanistic practical attack. Here's Bertalanffy. Organicism vindicates the autonomy of life, denied in the mechanistic conception, and remaining a metaphysical question mark in vitalism. Okay, so that's the way they're thinking about it. And I figured I would mention also, just to put some flesh on the bones, okay? These people had a set of concrete ideas. Of course, they disagree with each other, because otherwise there would be no reason for them to discuss with one another, but we can identify a set of common commitments, okay? And some of them were actually formulated as principles or even laws. So this connects nicely with the discussion we were having a moment ago before coffee about what will be vital laws. So at least the organicists were thinking about laws of method. So here is E.S. Russell, who provides what he calls these two laws of method. The first one is the idea that the activity of the whole cannot be fully explained in terms of the activities of the parts isolated by analysis. That seems like a general sort of statement of anti-reductionism. Okay, and if you look at the writings of other organicists, you have similar claims being made by others. So Needham says that the whole does not denote anything added to the parts. When we talk about the whole is greater than the sum of the parts, like an entelechy, right? So you have him clearly separating himself and the movements from Driesch, but refers simply to complex organizing relations between the parts, okay? So what makes the whole a whole is not anything added to it in terms of materials, but organizing relations. And here we have Paul Weiss. So Weiss and Bertalanffy, both Viennese, and Weiss actually at the end of his career developed a very, very interesting sort of systems philosophy of the organism, where he says, you know, we need to understand the whole, we need to supplement the statements that we get about individual parts by additional statements that describe collective behavior, okay? And the second law of biological method from Russell: no part of any living unity and no single process of any complex organic activity can be fully understood in isolation from the structure and activities of the organism as a whole. So not only can you not understand the organism in terms of its parts, but the parts cannot be understood in isolation from the whole, okay? So it's kind of the inverse of that. And again, you see that in the writings of other organicists of the period, okay? So coalescence or convergence with regards to these two basic ideas, okay? And there are many others, okay? So, and many of these commitments, I think, are commitments that many people today want to defend, which is one reason why I think philosophers of biology, even if they have an aversion to history, should care about these forgotten people, because if you want to argue for the centrality of the organism, it's become a big deal, you know, then you have allies in the organicists wanting to say things like Bertalanffy, where he says the concept of organism is as central in biology as the concept of energy is in physics, or when Russell says that any biological theorizing has to begin and end with the organism. The role of organization, the importance of a theoretical principle, again, something that we find all of the organicists basically saying, you know, that is the central problem in biology. Why? Because that is what distinguishes the living from the non-living. That is what takes the place of the vital principle, okay? So instead of appealing to a vital principle that is metaphysically questionable, what you say is it's organization that makes the difference, and then the next question is, what is organization, right? As you can think about their research program as exactly doing that, trying to work out what is organization. A lot of my work has actually been looking at the problems with machine metaphors and machine analogies in biology, which are rampant. It turns out that if you look at this work 100 years ago, the people are saying exactly the same thing. So again, useful allies, at least for me. right? So would you saying that the machine analogy has put us on the wrong scent? How long are we to persist in refusing to look at sheer hard facts in the face? And he says, in the interest of a 17th century analogy, right? And Bertalanffy saying that we cannot speak of a machine theory of the organism, but at most of a machine fiction, which is a deeper claim than it looks. It's suggesting that maybe a heuristic, a machine heuristic is actually useful, okay? And process, right? Another recent sort of development in field bio, you have again, the organicists making that case, which you think about organisms as events, something happening. Actually, before the analytic metaphysicians, already Woodger was talking about temporal parts and temporal differentiation, and that, you know, the organism today is not the same as the organism yesterday because it's a different temporal part. And Russell talking about life cycles. You know, we think about organisms as life cycles rather than as entities at a given time. Good, okay. Right, so in trying to understand what is that motivates these people and why they were defending the views, they were defending when they were doing it, I think it's useful to understand what was going on at the time. Okay, specifically what was going on in other areas of science, in physics. Okay, and so what you find again and again, and surprisingly it's just really something that you can bet on finding when you look at the writings of these people, are references to Whitehead. And not the Whitehead of process and reality, mind you, not the heavy-duty Whiteheadian metaphysics. There's no discussion of prehension and actual occasions and concrescent, but rather the middle Whitehead, the 1920s Whitehead, when he moved to the US and was, especially the book Science in the Modern World, where he's basically, Whitehead is trying to wrestle with what is going to be the new philosophy of nature in the light of the revolutionary developments in physics. What is going to be the new view of nature that we need to develop, given the fact that 19th century physics has collapsed and quantum mechanics and relativity theory have thrown everything in the air, all right? And so interestingly, when you look at the writings of these people, right, there's a lot of references to Science in the Modern World, and I've tried to enumerate here the things that they pick up from Whitehead specifically to give you a more concrete idea. The first is the recognition that there's been an erosion of mechanicist and materialist natural philosophy, which had prevailed in science since the 17th century. The demonstration that everything in the world is connected to something else, right? So we need to have some notion of interrelatedness and organizing relations. There are no absolute boundaries, no isolated parts. The abandonment of strict determinism and predictability in nature, and the possibility of a role in mind in nature. And a restoration of the human observer. Now, this one is kind of more parenthetical because the organicists don't necessarily take that up. I mean, you have people like Agar and Lilly, who are of the same period, who do. I would call them Whiteheadian philosophers of biology because they have a sort of commitment to this panpsychism that we tend to associate with Whitehead. But I mean, in general, you can say that these are important ideas for the organicists, okay? And the really interesting thing also is that it's not just, of course, Whitehead provides some sort of he is providing a way for the biologists to understand why we should care about the new developments in physics, right? And so that encourages many of these organicists to read what the physicists are saying, especially in quantum mechanics, about the nature of nature. And so when you open up the books, these important books by the organicists, for example, this one from Russell, The Interpretation of Developments and Heredity, this is where I quoted the two methods, the two laws of biological method. So if you look at chapter 10, which is where he begins to talk about the organismal, of course, read here, organicist point of view. You can't read that, I'm sure. I was expecting to have a larger projector, but no problem. I'm not going to read all of it, but I have the page of it here because he begins by talking about how materialism as a philosophical doctrine has long been dead, he says, and as a scientific method, its limitations are now becoming apparent, even in physics, in which they originated and won their most striking triumphs. These simple mechanistic principles are proving inadequate. And then you have two nice chunky quotes by Whitehead making that point, right? The first one about how Whitehead in Science in the Modern World says, the progress of science has now reached a turning point. The stable foundations of physics have broken up. And for the first time, physiology is asserting itself as an effective body of knowledge as distinct from a scrap heap. The old foundations of scientific thought are becoming unintelligible, and then he says time, space, matter, material, ether, electricity, mechanism, organism, configuration, pattern, function, all require reinterpretation in the light of the new physics, okay? And then the other one, which is quoted even more frequently by the organicists, the appeal to mechanism on behalf of biology was in its origin an appeal to the well-attested consistent physical concepts as expressing the basis of all natural phenomena, but at present there is no such system of concepts. And the reason the organicists love to quote this is because I think it reflects something that still exists today, which is this sort of physics envy that biologists often have. If you want to be rigorous, you do what the physicists do. And 100 years ago, you have Whitehead saying, you can't really do what the physicists do anymore because they don't know what they're doing. So you're basically, you're liberated. It's under a sort of an emancipation. You can, not only are you liberated, but that perhaps the physicists should follow us because we've been thinking about interrelatedness and wholeness and anti-reductionism much longer than the physicists. So this, I think, is one of the key motivators for these people working around 100 years ago. Okay, and so there's reference who I already mentioned to Whitehead. There's a footnote to another physicist, Eddington. I'm not going to read it to you, but basically Eddington is saying determinism has failed in physics and it's probably not going to come back. And again, that's something that's good news for the organicists because the organicists were keen to develop a theory of life that would not rely on deterministic concepts. Okay. Russell is not the only one. So Woodger that came up before. So this may be perhaps the sort of magnum opus, the most important one, I would say perhaps the most important work in of the organicist period. Is a 500-page sort of tour de force called Biological Principles, published in 1929, where Woodger basically analyzes all the antitheses that he finds in biological thoughts and tries to resolve them. And the really nice thing is that already in the preface, he doesn't waste any time. As you open the book, the beginning of the book starts with this striking analogy that you'll never forget once I describe it to you. He says, modern natural science may be likened onto a crab, which has grown too fat for its shell. The process of existence is slow and painful. The old shell, which has matured and hardened for some 300 years, has done good service. No wonder the crab is loath to part with it, but it has already begun to crack and some bits have already dropped off. What should we do? Should the crab go on getting fat and take no thought for the raiment of the morrow, or should it resolutely face the situation, heave off the remains of the old shell with a sigh and set about making a new one? Okay? And this is a lovely analogy to describe how Woodger is basically portraying the situation in 1929, right? And as he explains in the next paragraph, the data of natural science constitute the meat of the crab, right? So the data has become too big to be encompassed in the shell, and the shell represents the general philosophical background and the theoretical basis upon which data has been systematized, right? The mechanistic, deterministic, reductionistic sort of worldview that collapsed with the new physics, okay? So a very, very striking way to begin his book, right? There's reason to be optimistic that the physicists have just undergone a revolution. It's our turn. And it's inevitable. It's a matter of time. It's not a matter of if, it's a matter of when. Right? So you get this again and again when you look at the writings of these people. So I just want to mention also Bertalanffy in his Modern Theories of Development, which was a translation of his 1928 book, translated and adapted by Woodger, by the way, just to show you that these people were not working in isolation. They were collaborating. And yeah, I mean, it's interesting to me that in the preface he's sort of acknowledging many of the other people that I've already mentioned to you as people that are basically making very similar claims. He says, you know, this way of thinking is in the air, he says. And you probably can't read that, but that's what he says here, right? And it's forcing itself upon the attention of independent authors. This is not something that historians have just looked back and said, something interesting was going. At the time, there was this recognition that something interesting was in the air and that a revolution was sort of imminent, right? And again, so Bertalanffy begins by talking about a crisis in biology, right? A crisis that has been partly a consequence of having too much data, not enough theory. Again, familiar to how we're thinking today about the role of theory in biology. And again, a place where, where he's talking about the collapse of the Newtonian science and how we need to draw on new physics. In fact, Bertalanffy has another paper from a bit earlier, from 1927, when he actually explicitly titled on, on looking at the meaning of the new physics for biology, and he was quite keen to draw analogies between biology and physics. I just want to give you one here. As in modern physics, there's no matter in the sense of rigid and inert particles anymore, right? But rather atoms are node points of a wave dynamics, he says. So in biology, there's no rigid organismic form as the bearer of the processes of life. Rather, there is a flow of processes maintaining itself in apparently persistent form. So you've got a processual view that is basically grounded, or at least licensed by the analogy with physics. Okay. So yeah, so this almost to say, this is explicitly a call for a sort of biological revolution. So here is Needham making that explicit. He says, modern biology is in a position totally different from modern physics. For although the latter has undergone revolutionary changes since the beginning of the 20th century, the former has not. Biologists are still following the ideals set for them in the great days of the last century. And then he says, if Thomas Henry Huxley could be revived, and he could revisit, he would find himself as much at home in biology today as he would be at sea in physics, he says. Woodger being more blunt, he says, if we are to make use of physics and biology, then please let it be the modern physics and not the warmed up corpse of Victorian speculation, which I love. Right, and just to show you again that these people were interested in collaborating and developing these ideas, so they actually came together. So there's a very sort of momentous, important, historically significant moment in the history of organicism, which is this Second International Congress of the History of Science in as you can see here, London, 1931. You probably can't read any of that, but I've just circled here many of the authors that I've just mentioned to you were all in attendance at the same time. And notice, what is the topic? What is the topic that they're to discuss? The relation between physical and biological sciences, some historical and contemporary, right? So it's very much at the forefront of how they're thinking about what they're trying to do. And Woodger here has a reference to Planck, right, where he talks about how basically using physicists as sort of authorities to license again their move towards a sort of a non-mechanistic view. I won't read that, but basically making the case that the notion of wholeness is going to have to come, it's going to have to be important. Planck says the whole concept of the last sentence, the concept of wholeness, which must be introduced as well in physics as it has been in biology in order to enable us to understand and formulate the laws of nature, right? Planck is saying this. Haldane sort of slightly ironically says, we should perhaps point out that if we accept Planck's contention, which I've just mentioned, mathematical physics can be regarded as a backward branch of biology. Why did he say that? Because we've been doing this for ages if we're biologists. Wholeness is not news for us, right? Which I think is kind of interesting as well, because remember, this is is at the end of 300 years where biologists were constantly having to justify themselves by following physics, and now we've got this very different situation. Haldane was actually quite bold. He has a sort of prophecy that he presents in this paper on the new physiology. He says, it is very likely that a meeting point will emerge between biology and physics. There's no reason for doubting that. But, he says, we can confidently predict that if the meeting point is found and one of the two sciences is swallowed, that science that is swallowed will not be biology, he says. Okay? And Needham, in his book Order and Life, where again you see references to many of the organicists, actually says the celebrated the revolution seems imminent. In 1936, what happened? Oh, let me give you another example of another person I haven't mentioned, Adolf Meyer-Arbach, who was based in Hamburg and then emigrated to Latin America. Meyer-Arbach takes Haldane's ideas really seriously, okay? So seriously, in fact, that he goes ahead and translates into German Haldane's The Philosophical Basis of Biology the year after it's published, and then including a very meaty sort of introduction to it. So this is the translation of Haldane's book, and this is what I think is his most important book from, I think, 1934, Idea and Ideology and Biological Knowledge, where basically Meyer-Arbach presents this idea of holistic simplification, basically saying that it is really the case that physics is a simpler form of biology, and that if we're going to have any reduction, it's going to be in that direction. And it argues that laws are more general and fundamental in biology than there are in physics, and says things like entropy, the concept of entropy can be regarded as a special case of biological disorganization. Interesting idea. Hasn't really been followed up, but an interesting idea. The principle of relativity is derivable perhaps from the relationship between organism and environment. Very controversial thing, again, thought-provoking thing to say. And the uncertainty principle is the consequence of the psychophysical relation. So he's trying to make the case that most of the developments in physics can be actually construed as sort of special cases of biology being more general. So it's a very different way of thinking about the relation between biology and physics that we have at this time. And there's actually an attempt to institutionalize organicism. So Needham spends about a year trying to convince Warren Weaver to give him money from the Rockefeller Foundation to establish in Cambridge an institute that would be devoted to the new biology, and was supposed to be called the Institute for Mathematical, Physical, Chemical Morphology, right, very interdisciplinary. And here are his notes where he had this idea of all the different branches of science that would be covered, and and there would be like chemistry and crystallography and theoretical biology with Woodger, right? And it was a failure. So Weaver wasn't convinced. He didn't fund this institute, preferring to fund what then came to be known as molecular biology. Weaver is very important in the history of biology, but not for this reason. Actually, he's important for having funded the kind of work that led to the institutionalization of molecular biology. So what happened to organicism? Well, let's have a look at them one by one, right? So what happens to John Haldane? Well, I mean, look, he died in 1936, so he just died. Okay, although of course, he was also obscured by his more famous son, J.B.S. Haldane, who I think was mentioned before, right? One of the founders of population genetics. E.S. Russell, again, died in 1954. Woodger, what happened? Well, interestingly, after publishing this big book on biological principles, he happened to find White's and Russell's Principia Mathematica and got completely obsessed and spent the rest of his life trying to develop an axiomatic framework for biology. Became a logician, lost interest in organisms. So now this is why Woodger has such a bad rap among philosophers of biology, because we only remember him for his axiomatic efforts, not for his earlier organicist work. Needham. Well, Needham had two Chinese PhD students coming to a lab in chemistry, fell in love with one of them, had an open marriage, so that was okay, and then ended up becoming the foremost authority in the history of Chinese science. Spent much of his later life developing multi-volume work on science and civilization in China, right? So again, moving far away, Bertalanffy decided after the Second World War that he would develop, he would generalize his ideas about the organism to all systems, and that's why he's remembered today as the founder of general systems theory much more frequently than he's remembered for his contributions to theoretical biology. Okay. And Adolf Meyerbeek had a complicated relationship with National Socialism, and so he never was able to rehabilitate his reputation. And there are many others, not just Meyerbeek, who shared the same fate. So this goes some way to explaining what happened to organisms. What is it? Why is it that after the Second World War, it sort of disappears from the picture, with a very few exceptions? And so you got this sort of really crazy situation where the new biology that eventually did arrive, which was molecular biology, of course, was actually not based on the new physics that had excited that whole generation of biologists, but was rather based on 19th century physics, right? With, of course, some cybernetics and information theory thrown in for good measure, but mostly a sort of metaphysical picture that you get from 19th century physics. And that has been observed by a number of people. So we have here, for example, David Bohm in the Wallington Symposia on Theoretical Biology. This is a well-known quote. It does seem odd that just as physics is moving away from mechanism, biology and psychology are moving closer to it. If this trend continues, it may well be that scientists will be regarding living and intelligent beings as mechanical, while supposing that inanimate matter is too complex to fit into the limited categories. So it's a completely absurd situation we find ourselves in, right? And here's Carl Woese in a really nice paper called A New Biology for a New Century, 2004, basically saying the same thing. Biology of the 20th century was in the strange position of having to confront itself to conform to a worldview, i.e. mechanicism, that 20th century physics was simultaneously in the process of rejecting. In a metaphysical sense, molecular biology was outdated from the onset. It's a very sort of interesting way of thinking about it. Okay, so what I want to do now is to tell you a little bit about the foundations of the molecular biology revolution. And Greg, how are we doing for time? Okay, well, it's not a lot of time. Right. So to understand why molecular biology did not end up relying on the new physics, we actually need to go back to the 1930s and to a very famous lecture or address that was given by Niels Bohr in Copenhagen called Light and Life. And in this address, Bohr for the first time suggested that his principle of complementarity that he had developed to make sense of the duality of light, wave-particle duality in light, perhaps has a role to play in other sciences, in biology and in psychology specifically. Not because there's an extension of quantum effects to biology and physics, that will be, or biology and psychology, that will be the Jordan's view, but more because there's an analogy. Okay, we find ourselves epistemically in the same situation in biology as we do in physics, in that we need two complementary descriptions of the phenomena. One reductionistic, one anti-reductionistic. You can't do one without the other. You need both, and they're not reducible to one another. So that idea becomes quite right? And they're both autonomous. So yeah, he talks about how, just as in physics, we cannot account for atomic phenomena without experimentally interfering with them. In biology, any attempt to trace, say, the atoms, to analyze it mechanistically, is incompatible with keeping it alive. You know, you want to understand how a cat works, and you break up the cat, you no longer have a cat, right? You can't keep the thing that you want to study if you study it mechanistically and reductionistically. Okay. So this is a quote to making that clear. I will skip that, as I just already explained that. And then, yeah, he goes on to say that we should think about life as a sort of an axiomatic principle, which is actually an idea that you also find in Haldane. And actually, I found evidence that Bohr got these biological ideas from his father, Christian Bohr, who was a physiologist, and Christian Bohr collaborated with John Scott Haldane. So there's actually an interesting connection with organicism, and I'm looking at that in the written version of this. So in attendance at this lecture was a physicist that became really an important figure in the history of biology, Max Delbruck, who on the strength of this lecture decided to reorient his career and become and turn to biological problems. Specifically, then later said exactly that. And he hoped that that paradox would emerge in biology, similar to the one that Bohr had solved for physics in 1913 with the model of the atom. He says that's why we should turn to biology now. If Bohr was right and life was not reducible to physics, then the rigorous pursuit of a reductionist research program in biology, pushed to its limits, should uncover the need for complementary mechanical and teleological descriptions of biological phenomena. Notice what he's saying here. All we need to do is to push the reductionist approach far enough until the subject matter itself will cry out for a complementary form of explanation. We're gonna force a paradox by going full on in a reductionistic mode, looking at life, which is exactly what he then goes on to do. So he's got this whole research program, which is nicely presented in this paper, A Physicist Looks at Biology, from 1949. And there he talks about how it is likely, or it may turn out, that we may find that certain features of the cell, like replication, are in a mutually exclusive relationship with what we know, what quantum mechanics tells us, and that a new language is needed, right? And that this will present a limitation to the applicability of present-day physics, right? And that we might, as I say, find features that were not reducible, okay? So this is an important motivation for Delbruck, okay? And of course, Delbruck is remembered especially because his ideas take an important, or his model of the gene plays an important role in showing this very, very famous and very widely read What is Life, right? And if you look at the actual content page of What is Life, you find actually that there's a whole chapter just called Delbruck's model, discussed and tested, and a big chunk of the book is discussing Delbruck's model of the gene. This was a model that Delbruck had presented in a paper, so-called Three-Man paper, or the Green Pamphlet paper, which is a paper that he co-authored with Timofey Frysovsky and Carl Zimmer. So Schrödinger took a lot of things from this paper. One of the things that he took was the idea that the gene can be understood in quantum mechanical terms as a stable association of atoms, which are brought together by solidifying covalent bonds, and which can be, and where you can also think about mutation and alleles as a consequence of isomeric configurations of the atoms. Okay, so he's basically using quantum mechanics to make sense of the gene in a way that was influential for Schrödinger. In fact, Schrödinger goes as far as to say that if the Delbruck picture of the gene failed, we should have to give up further attempts. And in many ways, the phage group was a success, right? Delbruck started working on bacteriophage viruses as a model instead of the Drosophila, that had been the traditional view. Assembled a group with people like Salvador Luria and Alfred Hershey. It came to be known as the phage group. Here is a picture of it, and which was designed or modeled in strict imitation, as Delbruck would later say, of the Copenhagen spirit in physics. So he saw himself as emulating what had happened in physics. And there were a bunch of, a lot of things happened to institutionalize what Delbruck was doing. And, when you look at histories of molecular biology, the phage group is considered to be one of the major sort of motors, engines that drove the discoveries that led to molecular biology. So in that sense, it was a success, but his search for a paradox was a failure. He never found that paradox that he was looking for, that had excited him, right? In fact, already by 1950, it's sort of given up. It sort of moved. He said, well, he thought that it was unlikely that we would find a paradox looking at information transfer and replication and genetic information, and moved his attention, shifted his attention elsewhere. And then when Watson and Crick discovered the double helix, or provided the structure, Delbruck wrote to Bohr saying that the discovery may rival Rutherford in 1911. I imagine, I'm not a historian of physics, but I guess that is, I don't know what happened in 1911, but I guess important. But the key point is that later Delbruck was forced to admit that this big discovery that had led to molecular biology had solved all the mysteries of genetics in terms of classical models and theories without forcing us to abandon our intuitive notions of truth and reality as in the new physics. So here's the sort of irony, right? That Delbruck is moved by this anti-reductionist urge to show that Bohr was right about biology, and he helps bring about that revolution, but when it finally comes, it's a reductionistic revolution, okay? So in that sense, it was a failure. So when this Festschrift came out, commemorating Delbruck, notice the title, Phage and the Origins of Molecular Biology. The introductory chapter by Gunther Stenter, who was one of Delbruck's students, is waiting for the paradox, ironically, waiting for the paradox, which never came, basically. And the interesting thing is that no one took that stuff seriously, not even in the group, right? So most of the people who were inspired to work with Delbruck had been inspired to work with Delbruck because of Schrödinger's book, not because of Bohr's sort of claim that there's a paradox to be found. And none of them shared the conviction. Luria thought that Bohr's views were tainted with idealism. This is a quote. Hershey said, quote, "He never liked the complementarity double talk." And Benzer and Watson denied ever being influenced by Bohr's ideas. And there's only maybe one person was influenced, which is Gunther Stent himself. But Gunther Stent himself says, he confessed that he never really understood just what Max had in mind when he used the term. So it's really a bit of an indictment to that program, right? So the organicist revolution fails. The attempt to develop an anti-reductionist sort of Bohr-inspired revolution also fails. And what actually ends up winning the day is a sort of a much more late 19th century physical picture that is still with us today. Okay. And in fact, the view that we get of molecular biology, the view of the cell that we get today is not the one that we get from what Delbruck thought. Actually, it's the view that you get from what Schrödinger thought. Okay, so if you look carefully about what Schrödinger argued, and Schrödinger, of course, was very, very critical of Copenhagen. He called it a sham philosophy. He said he was very, very critical of Bohr and never accepted, like Einstein, that Copenhagen was the right way to think about quantum mechanics. And so his view is a very different one. And, and the really important thing is that, of course, quantum mechanics is important for Schrödinger, but it's in life. But what it gives Schrödinger is something very different, which is stability and rigidity, right? So if you look at what is life, what you find is that Schrödinger is appealing to the covalent, the Heitler-London theory of the covalent bond of quantum mechanics to explain how it is that the genetic material is rigid enough to withstand the stochastic effects of Brownian motion. Okay, basically, this is a bit of a, I'm going to have to come to a close. If I had more time, I would expand on this, but I'm guessing we should leave enough time for Q&A. Basically, yeah, so basically the legacy, right? What you find when you look at molecular biology today and you see people talking about cellular circuits and molecular machines, that's not the view that is a result of the work of the organicists, which were of course forgotten. It's not even the view that you get from Delbruck, but rather is coming from Schrödinger and then from those who were inspired by Schrödinger, like Jacques Monod. So I don't really have time to talk about that, but I just maybe mention that Schrödinger is the first person to talk about a code script for development, right? So the idea of a genetic program that you may be familiar with, right? That you can think about development deterministically as the execution of a set of algorithmic instructions that are in the genome is something you already find in Schrödinger 17 years before it was coined by Monod and Jacob in 1961. The idea that molecular interactions are based on the rigidity and the specificity of the molecules, which is so important to how we think today about molecular reactions, is again something that you find in Schrödinger, right? And so a claim I think could be made that there is important physics in the new biology, but it is not the physics that had inspired the organicists. Okay, I've only got to about half of my talk, but I think I'm going to end it there so we have time for Q&A. Right, thank you. Yeah, so I just want to say that even though we have this mechanical view of the cell that is, again, today very prominent, there are very interesting developments that are happening. Okay, if you give me 2 minutes, I'll give you a slightly longer story so that I can contextualize it. So if you look at the contemporary view of the cell, this is the view that you get. Okay, I'm just going to start here again. Sorry, no, after Bertalanffy. Okay, so you got this view, right? This machine view of the cell, okay, which is everywhere. And you got all these metaphors to molecular machines. There's dominant, and you got all these different ways in which the machine analogy is used in molecular biology, right? And at different levels of organization. And you got, sometimes you're talking about cogwheels, other times you're talking about computers, right? And you got that as the dominant sort of metaphysical picture, which is, say, you can find in Monod and in Schrödinger already, right? And that kind of way of thinking about, protein interactions, the sort of circuits, okay? That seems today still to be the view, right? And what I had is a reference to this very, very, very famous paper called The Hallmarks of Cancer, super influential in cancer research. And I know that because it's got 39,000 citations. And in this paper, published in 2000, the researchers say that the solution to cancer is going to be to identify the circuit of the cell and resolve it. And that's going to be the solution. Okay, so here is a diagram that they use to look at how we should think about molecular interactions. And here's what they say. We should understand as circuits, we should think of proteins as transistors and so on. And they say 2 decades from now, this is in 2000, having fully charted the wiring diagrams of all the signaling pathways, it will be possible to lay out the complete integrated cell upon its current outline. And then we will be able basically to solve cancer. Okay, this is in 2000. Then in 2011, they write a follow-up paper called The Next Generation, the Hallmarks of the Next Generation, cited even more times, 63,000 citations to this one. And there again, you find them using circuitry metaphors to describe what we need to do to solve cancer. But the really interesting thing is that if you look at the very latest iteration, so the third part, I guess the final part in this trilogy in 2022, Hallmarks of Cancer, New Dimensions, there's actually very little references to circuitry. They've sort of given up on thinking that this is the way that we should think about the future of cancer research, right? So if you just do a quick count, what you find, here is the count, that you got in the first one, 28 times, and the third time, 34 times, and 4 times only. So this is just, again, a little bit of evidence that maybe scientists are becoming aware, okay, that this may not be the best way to understand how proteins relate to one another. There's a whole story to be told about why this picture fails. So getting to your question, Andrea, so what's interesting is that the reason why that picture failed is coming to us from physics. Okay, it is developments in condensed matter physics and self-organization and statistical mechanics that are enabling us to understand why that mechanical picture fails, to the extent that it does fail. Okay, it may be useful in some isolated cases, but in general it fails, right? So if I had more time, I will tell you about how the sequence structure function paradigm is collapsing. We don't no longer think that the amino acid sequence is sufficient to allow us to characterize function, right? That's a mechanistic view that is empirically no longer well supported. And most interestingly is that we're discovering that a lot of parts of the cell are made up of things that we don't know what they are. Physicists don't know what they are. They sometimes behave as liquids, other times they behave as solids. They call them biomolecular condensates. They are not membrane bound, they bud off, they do weird things. And they seem to be involved in many different functions, okay? And the physicists are saying, this looks like a new state of physical matter that we're discovering in the cell. So it's a really fascinating and intriguing and exciting example of how maybe the new physics will end up having an important role to play as it replaces the machine view, right? And so you've got all these, journalists writing about how these shape-shifting blobs are ruling biology, and cell biology befriends soft matter physics, and how phase separation is revolutionizing biology, and you're having this replacement of this view with this view. Right? Which is one that forces us to give out that machine view with one that looks more like this, like a sort of a lava lamp, right? So this is one example. I could talk also about self-organization, but I won't. But that would be another example of how physics, in this case non-equilibrium thermodynamics, is suddenly becoming relevant. I mean, it wasn't for 50 years. I mean, Prigogine had done his stuff in the 1960s, but it's only now that we are having cell biologists talking about the importance of self-organization in the cell, say. Okay, so these, I think, are reasons for us to be optimistic, and why I had the question mark that maybe the organics revolution is coming. It just took 100 years longer than we thought.